My name is Lloyd Pelham. I'm the CTO of Vnomics, and Vnomics runs an IoT software as a service for commercial trucking. And we help those commercial trucking fleets save fuel by optimizing their fuel spend. Just out of curiosity to try to get a better sense of who's in the audience, who has had familiarity with the term digital twin before? Is this a familiar thing? Okay, just one or two. Okay, good. Hopefully by the end of the talk, we'll have that straightened out in terms of more familiarity. What about IoT system deployment? Have folks had experience with deploying IoT systems or using data coming from IoT systems to help make decisions and optimize things? Okay, a few more. All right, so again, on that front, hopefully we'll do a little better in terms of understanding by the time that we're done. So let's take a look at where we're gonna go today. So for today's topics, the first thing you really want to start with, and this theme actually has come out in some of the earlier talks, is targeting your business value. And in particular, you have to be careful to avoid false opportunities. In commercial trucking, as we'll see as I'll lay out some of the statistics, there's some operational expenses that are very hard to get your hands on. And you invariably want to stay away from those and focus on the things that you're going to be able to do a better job in terms of putting impact or return on investment around. So targeting that business value and understanding that there's some that are better than others is something we're going to get into and hopefully shed light on what you need to do to try to make that come out the way you want it to. Once you have a clear understanding of where you're going and what you're trying to do, well, then of course it's time to bring in the technology. But you sort of want to hesitate and don't do that right away until that you have proven that your data is going to be sufficient to create clarity and visibility and the control that we're going to get into in this particular expose of the application. In particular, a lot of people get into a very quick identification of wanting to use particular machine learning algorithms and deploy technology stacks. In fact, it was touched upon in the last talk as well. You want to make sure that you focus on the data to begin with, tie that data back to the business value that you're trying to create, and make sure that you have clarity there before you start delving into all the different choices from a technology perspective. Because if you don't get that part right, the technology is really not going to help. And then that really leads very quickly into making it real, and then the considerations of how you build one of these systems effectively to give feedback and control to the people who are going to be able to make a difference with the insight and information that you're producing, so that you're making a big impact, and ultimately you're tying all the way back to that business value that you started with as wanting to capture. So targeting the business value, this statement sort of sums it up. So capture that value by employing the means to optimize very significant operational expenses. And in fact, in our case, our whole systems lease in life is focused on fuel optimization in commercial trucking. And as you'll see as we go through the details, there's a very significant operational expense. It can make or break profitability in a lot of these companies. Everybody's aware of how fuel prices from a commodity perspective rise and fall with oil prices and things like that. And so having a very tight control over that within a trucking fleet is an absolute imperative. And so these are the kind of operational expenses that you want to make sure that you have the kind of optimization that I'm going to go through tied to. So let me give you a little insight. Commercial trucking in the United States. So it's big. There's been a couple talks already today that have sort of poked at different parts of this, but in particular today I'm speaking about Class 8 tractor trailers. There's one of those Class 8 tractor trailers for every 100 people in the United States. I mean, you get the sense of this when you're out and about on the road or any one of the highways. They're all over the place. You see them constantly. But there's over 3 million of these tractor trailers on the road in the U.S. alone. And so if you start to look at this from a flow perspective, there's $160 billion in diesel fuel purchased per year being burned by this network of trucks within the United States. And if you flow back to what that represents from a per truck perspective, each one of those trucks is burning $50,000. And again, this you can imagine that goes up or down based on fuel prices, cost of oil. But in general, it's that kind of number that we're dealing with in terms of fuel flowing through these trucks. So what I want to point out, and again, this was what we talked about when we kicked it off here, is that this is a massive optimization opportunity in terms of harnessing savings or operational efficiency within that flow of fuel going through all these tractor trailers. So if we dive into one of the trucks in particular and look at its expense profile for a given year, again, we're talking about, this is the part where we're trying to make sure that we're targeting the business value correctly. So $130,000 a year in terms of expense profile for one of these assets in a year. And if you walk your way around the wheel here, one of the things that I found interesting about the expense profile of one of these trucks was that drivers' wages and benefits are on a par with fuel. And in fact, depending on what fuel cost is at a given moment, the fuel is actually more expensive than the drivers and their benefits associated with moving the truck. I guess that dovetails into a whole nother conversation about automation. And of course, that's being talked about a lot today as well. And you can clearly see why automating these trucks in terms of attacking that blue expense. And also we'll talk more about the efficiency of how to run one of these vehicles and how the drivers are tied very directly into the efficiency of these vehicles and how automation is going to make a huge impact on this expense wheel as well. But before we delve into the fuel part of it, I wanted to take a quick aside and talk about the maintenance piece. Now you can see that the maintenance piece is about 10% of this. When Vnomics as a company was first spun off of some research done at the Rochester Institute of Technology, they had a series of contracts with the Office of Naval Research to do predictive maintenance kind of machine learning applications. Condition-based maintenance for a vehicle going into combat so that they could try to predict whether or not that vehicle would break down or not. And of course, in a military operation, that's a very serious thing. So there was that kind of technology being developed at Vnomics. Well, Vnomics was spun off to go work in the commercial trucking industry or target the commercial trucking industry. And of course, the first application that everybody thought about was attacking that green, roughly 10% cost profile of maintenance and repair on these trucks. We were going to try to predict breakdowns in commercial trucking. Well, as it turned out, that was a bad idea. The reason being is that a lot of trucking companies, especially the bigger ones, will run fairly new trucks. They all have warranties. They must perform preventative maintenance on these trucks in order to keep the warranties. So even though that 10% represents, on the order of about $1,000 a month of cost that's flowing through those vehicles, it's really not variable. It's not. We don't have leverage within the machine learning realm to try to reduce that significantly, even if we can predict odd breakdowns of these trucks within operation. And so that's what I mean about being able to focus in on a specific value proposition that really makes sense. It seemed like this was going to be the right one, and we could have gone through lots of trouble deploying all sorts of technology, trying to attack it, and not really understanding from a domain perspective that it wasn't really there to be had. And so as a result, let's attack this beast instead. Let's attack fuel, and you're going to see how this is a much more promising place to go and apply the technology and make a return on investment. Quick question. I'm sorry. So that's a good point. So how much of the maintenance is scheduled versus unscheduled? One of the things is if you're running a fairly new truck under warranty, it's mostly scheduled. It's mostly preventative maintenance, and so you're investing in that to try to keep the truck up in good repair and follow the manufacturer's guidelines. In the case where the truck gets very old, then it sort of shifts and becomes less preventative and there's more breakdowns involved that are certainly more costly. But that's sort of the long tail of the trucking market in terms of where the assets go after they're first initially deployed. Good question, though. Yep.
So how would that distribution occur for trucks? Would it be like 50% of you that are doing preventive maintenance as part of the 23, 30%?
It actually is it's even more complicated than that because the large logistics companies tend to run newer assets, and then when they reach a certain sweet spot within their life cycle, as an asset, they resell them into the market, and then that goes to a lower end of the market or a different use profile of the market. A lot of owner-operators will buy a used truck that's maybe 5, 6 years old, and they'll be the ones that will have to deal with that more unscheduled maintenance problem and the preventive maintenance. It's a little different than cars where, personally, I drive my car till it dies, so if you catch me at that later 5 years of my vehicle, I'm dealing with a lot of repairs. But other people lease a car and they only run it for 3 years. They do the preventative maintenance and then they're out of it. And so that's the kind of customer that you want to be careful of, because they have no interest in trying to shave their maintenance cost, because they really don't have the responsibility for it. They're leasing a vehicle and they're going to get rid of it. They already intend to get rid of it at the end of that cycle. And so that's the kind of nuance in these expenses. You have to be careful that you're really targeting the right business value and applying the technology to make a bigger impact. Good questions, though. That's the essence of why we were working through this wheel, and we were in the wrong spot of this expense wheel. We had to get onto the right stuff. So let's talk about that. So I want to introduce the digital twin. So here we have a 2013 Kenworth T680 tractor. You don't have to be in the trucking business. It's a nice shiny yellow truck, very expensive, a workhorse within the industry for moving freight, fuel, anything that you would have within these Class 8 kind of truck applications. The thing I want to point out is that this truck is singular in its being, right? Like, it has this particular vehicle identification number. It has a certain amount of miles on a given day that we're looking at this truck, and it has a certain emissions control system that's on it. It's very specific in terms of what a 2013 Kenworth looks like. What we're going to do as a concept is introduce a digital twin. This is a model that mimics what is going on with this 2013 truck, and we're going to have one of these models for every truck that's in our network or in our concern. And then we're also going to expand that out, because as Kenworths go and as 2013 Kenworths go, there's more than one of them. So we can also benefit from the fact that we are a member, from a digital twin perspective, of a class of models that track all of these 2013 Kenworths, or Kenworths in general, and we can gain further insight from the model of one to the model of many. So far, so good? So what is a digital twin? It's a model. I'm going to use this term interchangeably between digital twin and model. And that model is focused on a chosen set of characteristics about that physical asset. In today's discussion, it's that red portion of the expense profile, fuel. We want to optimize fuel. And so the way that we're going to do that is we're going to gain more visibility, we're going to have more control, and that's going to lead to the optimization and the performance enhancement of the fuel economy of this vehicle. So the responsibility of the digital twin is to do that improvement of visibility and control, so the optimization and the performance can follow suit. And in particular, the kind of insights that you can get from a digital twin model are things like how performant am I at this moment? Am I being operated efficiently? You can ask a question about, is my performance trend increasing or decreasing? So in other words, one of the ways that you can tell whether you should trade a truck in and buy a new one or keep it and keep going is by watching the performance trend on fuel economy. So invariably, as a truck ages and that emission control system gets tired and more costly to maintain, the fuel economy of a truck will invariably start to dip. And so you can use the digital twin and the insight coming from it to determine when you should get rid of a truck. One thing you can do. The other thing is it's very effective to be able to look at the digital twin and say, how are you performing in the respect of your class? And everybody can sort of visualize what that would look like. For every group of 2013 Kenworths, there's a bell curve of performance, and it's helpful to know, is this a mid-tier performant Kenworth, or is this an outlier? Is this one exhibiting exemplary performance or very poor performance compared to its class? And we want the digital twin to be able to convey that kind of insight. So once we've gotten that far, so in other words, we're targeting a very large expense of fuel, And we're going to apply this concept of the digital twin to model it. This is where we want to start to transition to say what technology is going to come into play, what's that digital twin actually going to look like, and what it's going to have to draw on to do the sort of things that I'm talking about. And so this is where you want to spend time digging into the sources of data that you have, making sure that the visibility and the control that you're going to get from the data sources that you have are going to be sufficient to solve the problem. That's before you end up deploying all sorts of technology, both in the cloud and on vehicles. You want to try to prove this ahead of time. This is a very key point, and it also came out earlier in the conversations that we had with the other presentations, is that domain expertise is absolutely necessary here. So you want people that are intimately familiar with the design of engines in these newer tractor trailers and pollution control systems and so on, to be part of the conversation that's putting together the data set and ultimately the modeling techniques that are going to be used within the digital twin to mirror that physical asset. And you want to do that ahead of trying to select whatever whiz-bang modeling techniques you're going to use. The honest truth is, data trumps models. Yes, if you get a really great model, you'll eke a little bit more performance out. But if you have data that is subpar, you can bring any model that you want into the party. It's not going to make a difference, or it's going to make very little difference. And so you got to get this part right before you start talking about modeling techniques. And then I already mentioned this. You really want to do this before you try to scale. You'll spend a lot less time and effort and money by doing it that way. So let's talk about data sources that determine fuel economy, because we really want to pay attention to these. This is the essence of what the digital twin is going to be about. I alluded to this earlier. Drivers make a huge impact on fuel economy. We all probably have the sense of this ourselves. Our cars may have, the newer ones have gauges in them that sort of show what your instantaneous fuel economy is. And I'm an aggressive driver, and so I get really bad fuel economy. But the same thing in these Class 8 tractor trailers. You can benefit by modeling or understanding within your model the idling behavior of that driver. Like, do they sit around all the time with the truck running for air conditioning or for heating purposes when they could be using auxiliary power? Are they shifting properly? Are they accelerating in a reasonable way? Are they speeding? And if they are speeding, to what extent is that affecting the fuel economy? This driver dimension is huge. It can swing the numbers by as much as 30%, depending on what's going on here. As we talked about a lot today, is shipping containers, but invariably when you're towing these shipping containers after they get off the boat, how full those shipping containers are certainly have an impact on the fuel economy. The environment, so humidity, temperature, all these things have an effect on what's going on. And the tractor itself, of course, the drivetrain configuration, the engine that's being used in this Kenworth we're using as part of our example today, it certainly has very specific characteristics that are important to the model. And then the routing itself. What task are you sending this truck on? Is it in the southwest of the United States in flat terrain, or is it in Colorado in the mountains? All of this stuff has to be taken into account because it's having an impact on fuel economy. This is the goal in terms of digital twin modeling of fuel economy. You have to bring all of this stuff to bear to really start out in the right direction for your modeling activity. So let's dig into that a little bit more. So commercial trucks, tractor trailers, they're orchestrated with sensors. In fact, there's a standardized sensor bus, lucky for us because it's been very convenient, to plug into that sensor bus, so you're getting a lot of operational data off the truck as it's being used about what's happening. And so all of that sensor data and about how it's being driven and how mechanically the truck is performing is flowing into this digital twin model. And its job basically is to answer the question, what could be happening at this very moment versus what is actually happening. We want to try to build the basis of understanding, here's what actually was measured out on the road in terms of fuel economy, but what am I going to have to do to improve that fuel economy, and at this very moment, what's happening that is not fuel efficient. And so if you look at actual fuel use and you subtract what could be happening from that, you end up with what we describe as a potential fuel use. And this is the fruit of the labor for the model. In other words, being able to publish and provide feedback about what could be happening is the essence of what the digital twin is being asked to do. And so it does that by learning each tractor's fuel map. Tractor, of course, dictates the fuel map. Different tractors, different kind of fuel use characteristics. And then the driver and the environment and the load, they all have very specific impact on the fuel economy, and that could be at any given moment as it's being used. You can imagine if I'm towing a very heavy load, the amount of fuel used in an acceleration event is very different than if I'm carrying a light load. And then this is essentially highlighting what I just described. It's that being able to publish what could be happening versus what is actually happening is what the model is setting out to do. And so just to give you some numbers as to what we see in practice, an actual fuel use might be coming up just shy of 6 miles per gallon, and the model may be spitting out the fact that you're wasting on the order of 4.5%, and so your miles per gallon could be in the 6.25 range. Mind you, these are big trucks, so these numbers are much smaller than what we're used to with our cars. And so you start to monetize what that impact would be for one particular truck, and you say, all right, we're on the order of thousands of dollars a year in fuel savings if we're able to recapture 4.5%, and that represents over $1 million a year for a 500 truck fleet. Now, a 500 truck fleet is fairly small. Some of the others are quite a bit larger, and the numbers get up into the tens of millions of dollars within a year even. So let's look inside one of these fuel maps. This is a little bit of a busy diagram. Let me walk you through it. So it's a 3D diagram. The x-axis is the wheel speed, the y-axis is the RPM of the engine, and the z-axis is the accelerator position that the driver has. The size of the dot is indicative of how much fuel is being used, and the color of the dot is the waste profile of what's happening. So a light colored dot is bad acceleration, and a dark colored dot is poor engine control or bad RPM or shifting control. And so a lot of information going on within this one picture. You can also see the fingers or the legs of this. That's the individual gears of the truck. So as they're going through and they're shifting, you kind of see that behavior in this graph. But in essence, I just want to show you the comparison. There's 6.8% loss on the Volvo picture on the left. On the right-hand side is the same exact truck, same exact operating profile being driven in a more efficient way. And you see all the color disappear. You see the acceleration in this particular case and the engine control are all much more tightly controlled, lot more fuel-efficient behavior. I want to step through because I'm sort of running out of time. Making it real. So you basically want to put this information that I'm showing you in the hands of the people that can make a difference. And you need to do that when they need it, and you need to do it in an unobtrusive manner, because if it becomes too foreboding, people don't like it, and it ends up not being successful. So to give you a system context of how that looks, you basically have machines and people working together with this model. We basically run the context into that model as well. So we need to know where we are, what the temperature is, what the speed of limit environment is, that sort of thing. Factor those in as well. And then we need to provide feedback to the drivers if they need it. So a fuel efficient truck in this case would be a quiet truck. No feedback required if things are operating efficiently. They're only given feedback if there's something going on that requires different acceleration, different shifting behavior to save the fuel. Then you want to analyze what's happening on every truck in particular in aggregate. Again, this is a theme. You see this in other conversations today. And that gives you not only a perspective about individual assets, but across the fleet. And then you want to also provide feedback. So in our particular system, as we're monitoring all this stuff in aggregate, we're also have triggers that reconfigure trucks potentially to do different things, because they all have computer systems that can be reconfigured, or to retrain models on a periodic basis that represent the digital twin modeling that I talked about earlier. In practice, I just give you a quick run through of the dashboard for our True Fuel system. What you see up here in the upper right is the system actually tracks the ROI for you, so it tells you how much you've been saving most recently in terms of fuel feedback and how much CO2 that represents. Then we also quantify the current opportunity in terms of what's going on within your fleet at this very moment. So difference in fuel economy and what are the factors that are attributing that difference, so you can attack it. and then also focus on specific machines and people and what the outliers are. What are my best trucks? What are my worst trucks? Who are my best drivers? Who are my worst drivers? I took the names off because everybody wants to be a great driver, but it's the guys that aren't so great that probably don't need to be publicized. But all kidding aside, the fleets use that information to incentivize the drivers that are doing very well and coach the drivers that are needing to improve. And the product also has some coaching features built into it so that that can happen more readily. So today's points, again, running out of time, I'll punch through quickly, but you must gain the control necessary to optimize those big expenses. That's the targeting the business value part. Make sure your data is sufficient to give you that control to optimize whatever it is you're focusing in on. And that has to do with making sure the signal to noise ratio within that data is sufficient to let these models do their thing. And that's where you bring the technology to bear and it works. And then providing unobtrusive feedback to the people in the places and the machines where they need it so that they can affect this positive change is how you get this to work at the system level. If there's a model running and it's providing predictions, but nobody's there to take advantage of those predictions, well, then it's not doing very much other than maybe having a prediction rate that somebody cares about in a lab. So you got to make it real. Thanks. I appreciate it. Okay. Any questions? Yeah.
How often is the driver machine linked together in these companies, or do they switch drivers and machines? I'm trying to delve into, is it difficult to separate what may be a machine versus a man problem if they're always driving the same machine and you're always getting a less than satisfactory?
Great question. So the question was, how do you separate the machine from the person if you always have different people on different machines? Is that essentially?
Or if you have the same person on the same machine,
Yep.
how do you differentiate what's the driving habit versus the actual mechanics of the machine?
Great question. So absolutely you can separate the two, and in essence that's what the True Fuel product does. The way that we do it is through the digital twin activity. So I remember I said we're modeling classes and we're modeling in particular. So if you got the one situation that you talked about where same driver, same truck all the time, we do get sort of a skew or a bias because that driver has a certain characteristic. But then we can look and bring information from the other 2013 trucks that are similar to what they're driving into the equation, and we can clearly see, okay, there's still improvement to be made because they may be driving poorly on that one particular truck. Same thing is if another driver gets into a truck. Yesterday, the truck was being driven very efficiently. That particular model understands that intimately then. When that new driver gets in and they're driving it inefficiently, they have the very recent experience, factored into that model of what's more efficient driving on that truck. And so all of that has to be built within the modeling of the digital twin. So regardless of who's driving it, you can separate the possibility of how it could be driven more efficiently and provide that feedback to the driver, regardless of whether it's the same driver all the time or the drivers are constantly changing.
I have a question for you. Go ahead. Yours are better than mine. So
Yeah. So you mentioned it in the beginning, kind of like alluding to like driver automation, like it's something that comes in the future. Is there anything that you've kind of done that's maybe halfway in between, whereas obviously very simple terms, instead of measuring whether a driver is accelerating efficiently or not, make it just so that they step on the gas and your system will make the truck accelerate efficiently?
Absolutely. Absolutely. So it brings up the thought of John Henry and the hammer, right? Like at what point is the human able to do better than the machine? And can we automate the whole thing, takes the human right out of it? I think what we found, there's already automated transmissions within the industry. So that what you just described, where you put the accelerator to the floor and regardless of how much you want it to accelerate, it's just going to follow a particular efficient profile. So this is already happening. What we find is that, of course, in automated trucking in the future, all of that will be part and parcel to what the automation is doing. But one side note is that in us looking at the data, the automation's not actually as good as the best human drivers still. So in other words, depending on the load conditions and everything and the driver's ability to anticipate what's going on, I find that the automated transmissions, if you have a poor driver, are helping you, but if you have a really good driver, it's better to let them drive the truck right now. I mean, we're essentially still flirting with, will the automation surpass the human performance? And I'll tell you today, in many of the trucks that are being shipped with automated transmissions, they're not quite there yet. What they're trying to do too is wrestle with another problem in the industry is they have a driver shortage, a lot of attrition. And so they have a lot of people that are inexperienced trying to drive trucks. And so the automation in that case definitely helps because they don't need to have as much skill to achieve a certain result.
One of the things that I've seen as a challenge is that when you try to give truck drivers feedback, they tend to adapt to it.
Yeah.
So there's like an example where they're not supposed to drive more than 10 hours a day. I'm sure you've seen
Yeah,
this one
absolutely.
where they say like after 10 hours a day, you're penalized for driving.
Yep.
But you're penalized for driving means you're going over 10 miles an hour, and it's measured once every minute at the top of the minute. So you have a bunch of truck drivers who are tired, who are going as fast as they can for 50 seconds, hitting the brakes, looking at their watch, waiting for the minute to trip, and then accelerating again until they get to the truck stop.
Yeah.
And it seems like whenever we build a system like this,
Yeah.
like maybe the automated transmission has an emergency button that lets you accelerate quickly and get out of a dangerous situation. You just have someone hammering that button.
Yep.
Have you found that when you present systems with this information, the system adapts to it and it undermines some of the potential upside?
Yeah, you bring up, this is really interesting stuff. So one of our larger customers had invested a fairly significant amount of money in these automated transmissions, and you bring up exactly what happened. Many of the drivers just turn the system off. They have manual overrides, almost all of them. And so the analytic problem changed from how efficient are my drivers to how often are my drivers using the automation and how does that automation compare to what my drivers are actually capable of doing. And so there's a struggle, a push-pull going on here about how to augment human capability in such a way that they believe that it's a helpful thing rather than a hurtful thing. And I think we'll always do better if we're erring on the side to make that automation a supporting system to try to make the whole thing work better overall.
All right. Thank you very much.
Thank you.